Hello. Hope everyone is doing wonderful and having a wonderful time and a wonderful morning. I am making sure everything's right. I think everything's right. Okay. So what we're going to do today, we're going to be doing more subnetting. Last stream there was a storm that was going on. There was weird things. I was cutting in and out and stuff like that. So because of that, we are going to watch the day 13 again. I don't know if we'll watch all of it. We're definitely going to watch like parts of it to kind of get us geared up, and then we will watch all of part 2. Of course, we will watch it at 1.5 speed because ain't nobody got time for that. Okay. If you haven't already, please subscribe to Tyler Lamond at Tyler Lamond. Man, I already have 208 subscribers. That's absolutely amazing. Thank you guys so much for the support. Yeah, I'm starting to kind of get my bearings down with like a lot of things. It's taking me a lot longer than I thought, but I do have plans to push out some new videos and stuff. I know that it's been a while since I've made a video, but I do plan to make more videos of those in the future. If you're not already subscribed to Jeremy's IT Lab, you definitely should. Great stuff there, and more than just this CCNA course that he has. Okay, it's just all of it is good. Other than that, we are going to be going over our work that we did yesterday. We didn't quite finish it because of the storm, so we're going to be working on that and figuring that out. Okay, and we're going to be doing some subnetting practice after we get through all the stuff. So without further ado, let's jump right into it.
Subscribe to follow along with the series. Also, please like and leave a comment and share the video to help spread this free series of videos. Thanks for your help. In this video, we will be talking about subnetting. Now, before I get into CIDR, let's review these IPv4 address classes, so we can then understand the need for classless IPv4 addressing. There are 5 classes of IPv4 addresses, 55.
So we have the 5 classes of the IPv4. The only 3 that you really need to know is A, B, and C. D and E are special, which we've kind of touched on a little bit in the past. But the CIDR is how many addresses are in each class. And from what I gathered, we basically repurposed that and changed it from being, I think it was like 8, 16, and 32, or no, 8, 16, and 24, because it was the different octets. That just wasn't a good, yeah, here it is, 8, 16, 24. It just wasn't really that great because it wasted a bunch of addresses. Okay.
24. So the first 3 octets are used to identify the network,
Which he'll
and
talk
only
about
the last
here in a
octet
second.
is used to identify individual hosts within that network. The different prefix lengths give different characteristics to these classes. As you can see, there are few Class A networks available, only 128. Actually less than that because some are reserved, like the 127.0.0.0/8 range, which you may remember is used for loopback addresses. Because only the first octet of a Class A address is used for the network ID, there are 3 whole octets available for addresses within each Class A network. So there are 16,777,216
Sounds
addresses
like a lot,
in
but
each
that
Class A
ain't
network.
nothing.
That is 2 to the power of 24, because there are 3 octets. 3 times 8 equals 24 bits. Class B addresses are different. There are more Class B networks, 16,384, but fewer addresses per network, 65,536, which is still very many addresses, of course. Finally, there are very many Class C networks, 2,097,152 networks, but only 256 addresses per network.
So the reason why these numbers are like huge, but yet not huge at the same time, 16 million Class A addresses sounds like a lot. But then when you consider that every major corporation, every business is going to have a website, and that means that every single one of those websites must have an IP address, that means that there can only be 16 million or so businesses with a website, right? Or if you think about any type of corporation, a device of any kind is always going to have an IP address. So as you can see that we burned through these pretty quickly. Not to mention that Class C was supposed to be for like normal folk, right? I wonder if this class A, B, and C was derived from like American driving license, because class A, class B, and then class C. I don't know. That's a total other thought I just had. But anyway, as you can imagine, the number of networks and stuff, like there's like this isn't even 1% of like America, and that's just not going to work. Like the numbers versus the amount of devices that were getting pumped out just did not work. So that's why we went to IPv6, which we'll talk about later. Let's continue.
So, how does a company get their own network address range to use? Well, IP addresses are assigned to companies or organizations by a nonprofit American corporation called the IANA, the Internet Assigned Numbers Authority. The IANA assigns IPv4 addresses and networks to companies based on their size. For example, a very large company might receive a Class A or Class B network. Remember, there are lots of available addresses to use for hosts in each Class A and Class B network, while a small company might receive a Class C network, because there are fewer addresses in each Class C network, only 256. However, this system led to many wasted IP addresses, so multiple methods of improving this system have been created. Let me give you an example of how this strict system of addresses can waste IP addresses. So, here are two routers. As you can see, R1 has 3 networks connected to it.
This is really important. This is how we
remember that routers
internet.
are used to connect different networks. So each of these links are separate layer 3 networks, different IP networks. R2 also has 3 networks connected here. Perhaps each of these networks will have a few switches, with many end hosts such as PCs and servers connected to these switches. However, there is one more network here. That's this network connecting these 2 routers. This is known as a point-to-point network, meaning that it's a network connecting 2 points. In this case,
and it's good to know that it's not just the router itself that has the IP address. It's every single interface that has the IP address.
R1 and R2. For example, this might be a connection between offices in different cities, let's say San Francisco and New York. So, because this is a point-to-point network, we don't need a large address block. So let's use a Class C network, 203.0.113.0/24. Because this is a Class C network, there are 256 addresses in the network. -1 for the network address, 203.0.113.0, -1 for the broadcast address, 203.0.113.255, -1 for R1's address, which I'll assign as 203.0.113.1, and -1 for R2's address, which I'll assign as 203.0.113.2. That's a total of 4 addresses used, and 252 addresses wasted. Clearly,
wow, that's a lot. That's a lot of addresses that could have been used for something that are totally gone. I'll let it keep
this
going.
is not an ideal system. Before introducing CIDR, here's another quick example of address waste. A company, Company X, needs IP addressing for 5,000 end hosts. This is a problem. Why? A Class C network does not provide enough addresses, so a Class B network must be assigned. Because a Class B network allows for about 65,000 addresses, this results in about 60,000 addresses being wasted. When the internet was first created, the creators did not predict that the internet would become as large as it is today. This resulted in wasted
fun fact, when I was a graphic design teacher at, I don't know, it was a few years back, we had a textbook. No one uses textbooks anymore, but we had a textbook that I found buried in a closet, and it was from 2004, 2006, and there was one paragraph about the internet, and it said some speculate that the internet will evolve to incorporate commerce. And that's basically it. That was what the paragraph talked about. And then it moved on to like something else. And I was like, huh. Yep.
address space, like the examples I showed you. And there are many more examples that I could show you. The total IPv4 address space includes over 4 billion addresses. And that seemed like a huge number of addresses when IPv4 was created. But now, address space exhaustion is a big problem. There's not enough addresses. One way to solve or remedy this problem is CIDR. The IETF, Internet Engineering Task Force, introduced CIDR in 1993 to replace the classful addressing system. With CIDR, the requirements of Class A addresses must use a /8 network mask, Class B must use /16, and Class C must use /24 were removed. This allowed larger networks to be split into smaller networks, allowing greater efficiency. These smaller networks are called subnetworks, or subnets. Let's look at an example of splitting a larger network into a smaller network so you can see how it works. Here's the same point-to-point network we looked at before. Previously, it was assigned the 203.0.113.0/24 network space, but that resulted in lots of wasted addresses. Let's write this out in binary. Here's the binary, with a dotted decimal underneath. Now, the prefix length is /24, so here's the network mask, also known as the subnet mask, 255.
Okay, so what he's talking about right now is that this /24 is each one of these. I don't know what they're called. Well, they're bits, but we're not counting whether or not the bit is a 1 or a 0. We're talking about whether or not the bit is being used. So that's 8, 16, and 24. So that's how we got the 24, which means that we have 8 blocks. Blocks, that's the word I was looking for. We have 8 blocks that are free. And that's why this is 255, 255, 255. Because when we're doing the binary, right, this is 158, 64, 32, 16, 8, 4, 2, 1. And all that adds up together to be 255.
255.255.0. Remember, all 1s in the subnet mask indicate that the same bit in the address is the network portion. In this case, I made the network portion blue, and the host portion is red. Well, how many host bits are there? 8, because it's 1 octet. So, how many potential hosts, or how many usable addresses are there? Well, the formula is this. 2 to the power of 8 minus 2 equals 254 usable addresses. What is the 8? Well, it's the number of host bits, which is 8 in this case. And why?
And if you're wondering why it's 256, because 8 to the 8th power is 256, not 255. It's because we count 0, because you have to count 0. That's very interesting, and that 0 is a very weird thing, you know? Like, yeah, but that's what it is. That's why it's 254. Trust it, don't fight against it.
I minus 2? Those are the network address and broadcast address. We can't assign them to a device, so we have to remove them from the number of usable addresses. So, we have 254 usable addresses, but we only need 2, one for R1 and one for R2. However, CIDR allows us to use different prefix lengths, so it doesn't have to be /24. Let's get some practice calculating the number of hosts within different prefix lengths. 203.0.113.0/25, 203.0.113.0/26, 203.0.113.0/27, /28, /29, /30, /31, and finally /32. I've put /31 and /32 in red because they're a little bit special. You'll see when you try to calculate it. So, pause the video here and try to calculate how many usable addresses are in each network.
So we did this last time,
okay,
right?
Let's check out the answers. So here is 203.0.113.0, but this time with a /25 mask. Notice that the network portion of the address has extended into the first bit of the last octet, and the mask in dotted decimal is now written as 255.255.255.128. I changed the color of the extra bit to purple, but it is part of the network portion, the blue part. If you don't remember how to convert from binary to dotted decimal, make sure you review that. It's very important for subnetting. Now, there are 7 bits in the host portion of the address, so the number of usable addresses is 2 to the power of 7 minus 2, which equals 126. Once again, we only need 2 addresses, one for R1 and one for R2, so we will be wasting 124 addresses. That's better than wasting 252 addresses with a /24 prefix length, but it's still wasteful. How about a /26 prefix length? Notice that it's now written 255.255.255.192 in dotted decimal, because 2 bits of the last octet are now part of the network portion. Since there are 6 host bits, there are now 62 usable addresses in this network. If we were to use a /26 network mask for the 203.0.113.0 network, we would be wasting 60 addresses. Getting better, but we can make this network even smaller. Now that you get the idea, let's speed it up. For a /27 prefix length, the mask is written as 255.255.255.224 in dotted decimal. There are now 5 host bits, so that means there are 30 usable addresses. As you can see, the address space is getting smaller and smaller as we extend the network mask.
What you need to understand, what was something that was really hard for me to understand, is that the network is like the top of the tree, and then all the addresses span down from that tree. So I had a hard time because like they're all IP addresses, right? A network address is an IP address, but inside of that network is a grouping of IP addresses that are usable. That is just the first one to label it. I don't really have an analogy that can compare the two together. But that's what we're doing right now. We're trying to figure out which network we should go to that's going to only have the smallest amount of addresses that we need in order to make this happen. This one's pretty easy because it's 2. 2's an even number. Okay, we have 2 points. We have 2 devices, 2 things that need an IP address. So in all reality, we're going to get down to where we either need 4 or 2. And you'll see why in a second.
Prefix length, the mask is written as 255.255.255.240 in dotted decimal. There are now only 4 host bits, So that means there are 14 usable addresses. After assigning addresses to R1 and R2, this would mean only 12 wasted addresses. But we can make this address space even smaller to make our addressing even more efficient. If we use a /29 prefix length, the mask is written as 255.255.255.248 in dotted decimal. Now we have only 3 host bits, so that means there are just 6 usable addresses. Again, after we give R1 and R2 addresses, there would be only 4 wasted addresses. If we use a /30 prefix length, the mask is written as 255.255.255.252 in dotted decimal. There are now only 2 host bits, so that means 2 usable addresses. So this is perfect. There are 4 total addresses. That's the network address, the broadcast address, R1's address, and R2's address. That means 0 wasted addresses. Before moving on to look at the /31 and /32 prefix lengths, let me clarify a little bit. So instead of 203.0.113.0/24, we will use 203.0.113.0/30, which is a subnet of that larger Class C network. 203.0.113.0/30 includes the address range of 203.0.113.0 through 203.0.113.3. Let me show you that in binary. Here is 203.0.113.0 in binary, the host portion all zeros. Here is 203.0.113.1. 203.
Where it gets confusing, and he's probably going to talk more about it in the next video and the video after that, is when we have subnets of subnets.
0.113.2 and 203.0.113.3. These are the 4 addresses in the network, these 2 being the 2 usable addresses, which are assigned to R1 and R2. So we took up 4.
Okay, so then we have 1, 2. Those are our only 2 options. So we can either have 1, 0, 2, because that 1 represents 2, 1, 2, 3.
4 addresses with this subnet. What about the other addresses in the 203.0.113.0/24 range? The remaining addresses in the address block, which are 203.0.113.4 through 203.0.113.255, are now available to be used in other subnets.
Yes.
That's the magic of subnetting. Instead of using 203.0.113.0/24 and wasting 252 addresses, we can use /30 and waste no addresses. Or perhaps there is another way to make this even more efficient. Let's look into it. If we use a /31 prefix length, the mask is written as 255.255.255.254 in dotted decimal. There is now only 1 host bit, so that means 0 usable addresses. 2 to the power of 1 is 2, minus 2 for the network and broadcast addresses means 0 addresses that we can assign to devices. So you used to not be able to use /31 network prefixes because of this. However, for a point-to-point connection like this, it actually is possible to use a /31 mask. Let's check it out. So here's the 203.0.113.0/31 network. R1 is 203.0.113.0, and R2 is 203.0.113.1. The 203.0.113.0/31 network consists of addresses from 203.0.113.0 through 203.0.113.1, which is actually only 2 addresses. Here they are in binary. There's 203.0.113.0, and there's 203.0.113.1. Normally, this would be a problem, because it leaves no usable addresses after subtracting the network and broadcast addresses. But for point-to-point networks like this, a dedicated connection like this between 2 routers, there's actually no need for a network address or a broadcast address. So we can break the rules in this case and assign the only 2 addresses in this network to our routers. Note that if you try this configuration on a Cisco router, you'll get a warning like this, reminding you to make sure that this is a point-to-point link, but it is a totally valid configuration. So once again, the remaining addresses in the 203.0.113.0/24 address block, which are 203.0.113.2 through 255, are now available to be used in other networks. But this time, we've saved even more addresses, using only 2 addresses instead of 4 for this point-to-point connection. People still do use /30 for point-to-point connections at times, but /31 masks are totally valid and more efficient than /30, so I recommend this method. But we still haven't looked at the /32 mask.
This
The
is the one that's
/32 mask
strange.
is written as 255.255.255.255 in dotted decimal, making the entire address the network portion. There are no host bits. If you calculate this using our formula, you will get -1 usable addresses. Clearly, the formula doesn't work in this case. You won't be able to use a /32 mask in this case, and you will probably never use a /32 mask to configure an actual interface. However, there are some uses for a /32 mask. For example, when you want to create a static route not to a network, but to just one specific host, you can use a /32 mask to specify that exact host.
Go one way, okay.
Anyway, I'll talk about that later in the course. Just know that /32 masks are used at some points, but you don't have to worry about them for now. Here's a simple chart showing the dotted decimal subnet masks and their equivalent in CIDR notation. That's right, the way of writing a prefix with a slash, followed by the prefix length, like /25, /26, etc., is called CIDR notation, because it was introduced with the CIDR system. Previously, only the dotted decimal method was used. Note that I've showed you only how to subnet a Class C network so far, but we will...
Okay, so this came first, and then we turned it into this. Because this only cares about... So basically what this /25 is the unusable, the bits that are frozen?
Look at Class B and Class A networks as well, with prefix length like /17, /11, /9, etc. I spent a lot of time on just that one example, but I hope you can see the use of subnetting, dividing a larger network into smaller networks called subnets. Instead of using the whole 203.0.113.0/24 network for the point-to-point connection, we can use a /30 subnet and use only 4 addresses, or even better, use a /31 subnet and use only 2 addresses. I'll give one more example of subnetting before finishing up this video. In the next video, I'll give you some practice problems and walk you through them so you can get some hands-on practice with subnetting.
We're going to do all of those, man.
So here's a scenario. There are 4 networks connected to R1, with many hosts connected to each switch. There are 45 hosts per network. R1 needs an IP address in each network, so its address is included in that 45 host number. You have received the 192.168.1.0/24 network, and you must divide the network into 4 subnets that can accommodate the number of hosts required. First off, are there enough addresses in the 192.168.1.0/24 network in the first place? So we need 45 hosts per network, including R1. But also remember that each network has a network and broadcast address, so that's +2. So we need 47 addresses per subnet. 47 times 4 equals 188. So there's no problem in terms of the number of hosts. 192.168.1.0/24 is a Class C network, so there are 256 addresses. So we will be able to assign 4 subnets to accommodate all hosts, no problem. Okay, let's see how we can calculate the subnets we need to make. We need 4 equal-sized subnets with enough room for at least 45 hosts. Here, I've written out 192.168.1.0 with a /30 mask.
Okay, so this is where we were. Dang it, dude. I just want to... This is what I want to do. Make it smaller. Yes, yes. Okay. So, this is where we were last time. Trying to figure it out. I was off by 1 address the entire thing. Now, my question is how did that happen? So we have 192.168.1.0/24. That's what this is. So then we needed to figure out the subnet for each one of these. So this is the network /24. We're basically doing the subnetting of a subnet. So that means we have 254 addresses to divide amongst all of these. So we need a total of 180 addresses because this needs 45, 45, 45, 45. Okay. So that's 90, 90, 90 is 180. So that means over here, we're going to use a /26 because that will allow us to hit the 45 area, our desired number of devices. So that means out of this, there are 2 addresses that we can't use, but that's fine. But what is... Give me a calculator. Jesus, that's big. What happened to the days of the calculator being small? I guess that doesn't exist anymore. Okay, you can't see it, but I have a calculator up. Okay, so don't be thinking that I'm doing this stuff in my head. So the number of bits that are taken up would be 8 plus 8 plus 8 would be 24, 25, 26. Ace, hold on. Sorry about that. That was my bank calling me about just stupid stuff. Do you want a loan? No, I don't want a loan. Go away. All right. Anyway, where we're at with this is that we need to figure out how many addresses are possible in here. So we have 8 plus 8. So we need to multiply this. By the host bit. So we have 6. So that means 2 to the power of 6 minus 2 is 62. So we have 62 bits. But if we're trying to figure out what the next subnet's going to be, it should be 64. So then this should be 65. So how the was I off? That means that this host should start at 65, not 64. I just made whatever mistake I made when I first did this. I'm making it again right now. Oh, here it is. 2 to the 6, 62.
The first subnet, subnet 1, is 192.168.1.0/26. What are the...
I don't remember him giving me the answer. Okay, why? Okay, that's
remaining
correct.
subnets? To help you out, here's a hint. Find the broadcast address of subnet 1. The next address, after that, is the network address of subnet 2.
Right, so the broadcast address of this should be 64.
And then just repeat the process for subnets 3 and 4. Post your answers in the comment section, and I'll also go over the answer in the next video.
Okay, what do we got? How is it 64? 64 is supposed to be the broadcast. Okay, hold on. We're going to take a screenshot of this. Oh, dang it. And then we'll go
192.168.
Oh, Photoshop, I hate you. Okay, I want to know why. Why is this not... Okay, let's watch the next video.
If you like these videos, please subscribe to follow along with the series. Also, please like and leave a comment, and share the video to help spread this free series of videos. Thanks for your help. In this video, we'll continue to learn about subnetting. Last video, I introduced why subnetting is necessary, and walked through a few examples. In this video, I'll try to give some more clear steps for solving subnetting problems. I've also decided to make one more video on subnetting, so this will be a 3-video series. So, what exactly will we cover in this video? We'll start with some subnetting practice questions, specifically for Class C networks, like last video. We'll start, of course, with the solution to last video's quiz question. After that, we'll look at subnetting Class B networks. The process is exactly the same, no matter what class of address you're subnetting, but it can be a little bit more difficult with larger networks. Class A networks will be covered in the next video, by the way. So, let's take a look at how to solve last video's question.
Yes.
I asked you to divide the 192.168.1.0/24 network into 4 subnets that can accommodate 45 hosts each. We found that a /26 subnet is the right size to fit 45 hosts, so we assigned the block 192.168.1.0/26 to subnet 1.
Yes.
If you don't remember how we determined that /26 is the correct size, take a minute to review the end of the last video.
We already did that.
So I asked you to find the remaining subnets. I also gave you this hint. If you find the broadcast address of subnet 1, the next address after that will be the network address of subnet 2. So, The network address for subnet 1 is 192.168.1.0/26. Here's 192.168.1.0 written in binary. Blue is the network portion, red is the host portion, and purple
is it because I forgot to add 0? Because 60... Because 64 added to 1 is 65, but 64 added to 0 is 64.
The part we borrowed from the host portion to add to the network portion. This allows us to divide the larger /24 network into multiple smaller subnets. To find the broadcast address for this subnet, which is the highest address in the subnet's address range, set all of the bits in the host portion to 1. Next, let's convert this to dotted decimal. It becomes 192.168.1.63. That's the broadcast address. So, the address range for subnet 1 is 192.168.1.0 through 192.168.1.63. The network address of subnet 2 will be 1 higher than the broadcast address.
Well, hold on.
The part we borrowed from the host portion to add to the network portion. This allows us to divide the larger /24 network into multiple smaller subnets. To find the broadcast address for this subnet, which is the highest address in the subnet's address range, set all of the bits in the host portion to 1. Next, let's convert this to dotted decimal. It becomes 192.168.1.63. That's the broadcast address. So,
God, I hate when that happens. Okay, hold on. So that means 1 plus 2 plus 4 plus 8. Yeah. Okay, that's making sense. Plus 16. Plus 32. 63. Why is this breaking my brain? Okay, I understand why it was 63. Which means that this right here, let's do it in a gross color. Oh yeah, look how disgusting that is. This disgusting turquoise. Okay. So that means that this that means that is going to be 64. So then if we add So then that means that if we add 64, which is what this is, to 63, we'll get 128. I got 127. Okay, let's keep going.
The address range for subnet 1 is 192.168.1.0 through 192.168.1.63. The network address of subnet 2 will be 1 higher than the broadcast address. So that means that subnet 2 will be 192.168.1.64/26. That's the network address, and here it is in binary. Notice that we changed one of the bits we borrowed from the host portion to a 1. So the network address is now 192.168.1.64, with all of the host bits set to 0. Now let's find the broadcast address. Change all of the host bits.
Because 64 is this block. All the other blocks are 63 when they're combined. Whoa, so does that mean... No, it doesn't. Never mind. Don't worry about... That was not an actual revelation. Okay, let's keep
bits
going.
to 1, and now let's convert it to dotted decimal. So the broadcast address is 192.168.1.127.
What? That's what I got. That's what I got just now. Look. Oh, check it out. Okay, It didn't pick up my calculator. Yeah, see, my calculator's right there. Boom. I don't use the display capture because it makes everything too big. And then I can't control the windows. Okay, so then that means that this right here is not 9, but it's 7. So then we just add another 63. No, we add a 64. It should be 90. Should be 92.
So that's the range for subnet 2. Add 1 to the broadcast address, and we'll get the network address for subnet 3. So that means subnet 3 is 192.168.1.128/26. Here is the network address in binary.
Fuck.
Again, notice this is 192.168. Notice that we changed one of the bits we borrowed from the host portion to a 1. So the network address is now 192.168.1.64, with all of the host bits set to 0. Now let's find the broadcast address. Change all of the host bits to 1, and now let's convert it to dotted decimal. So the broadcast address is 192.168.1.127. So that's the range for subnet 2. Add 1 to the broadcast address, and we'll get the network address for subnet 3. So that means subnet 3 is 192.168.1.128/26. Here is the network address in binary.
I missed it. Dude, I missed it again.
And the broadcast address. Change all of the host bits to 1, and now let's convert it to dotted decimal. So the broadcast address is 192.168.1.127.
So what did we add to the 64? Did we add 64? We added 64 because that's what it is. Okay, according to this right here. This is 64. The reason we're doing 62 is because we subtracted the network and the host. But in order to go to the next subnet, we need to factor in the network and the host. The host is always 0, right? So we're actually adding 64 to 0, which means that our broadcast is going to be 64. And if our broadcast... No, it's not going to be 64. It's going to be 63. Because we count 0. Which means that our next host is going to be 64. So we count 64. 64 is 1. That's because that's our first address. This is our network. Just like 0 was our network. So 64 plus 63. 1, 2. So 64 plus 64 is 128. Okay. Let's try it again.
So the address range for subnet 1 is 192.168.1.0 through 192.168.1.63. The network address of subnet 2 will be 1 higher than the broadcast address. So that means that subnet 2 will be 192.168.1.64/26.
Okay.
That's the network address, and here it is in binary. Notice that we changed one of the bits we borrowed from the host portion to a 1. So the network address is now 192.168.1.64, with all of the host bits set to 0. Now let's find the broadcast address. Change all of the host bits to 1, and now let's convert it to dotted decimal. So the broadcast address is 192.168.1.127. So that's the range for subnet 2. Add 1 to the broadcast address, and we'll get the network address for subnet 3.
That's why it's 8. Okay, hold on. 64 plus 63. Man. Okay. I think I figured it out. Let me walk through it one more time. I'm sure that people are tired of me doing this, but I gotta figure this out. Oh no, I wasn't expecting that. I don't want to write directly on it. No, stop. Okay. Now, I think I figured it out, and honestly, I probably made it more complicated than it should have been. So, the IP address of subnet 2 is going to be, oh, gross. Get this. Okay. Is going to be 192.1. Oh, do another point. 168.1.64. Now, the reason it's going to be 64 is because this right here is the network. Okay? Which means that 0.63 is the broadcast. I'll call it the bro. Okay? And anything in between the 0 and the 63 is going to be usable. Now, the reason, and this is where I'm getting hung up, the reason this is not 64 is because we count 0. Okay? If we started at 1, it would be 64. But we don't start at 1, we start at 0. So it's like it all got moved back by 1. Which means that this guy starts on 64. This is our network. Okay? Which means that we need to add 63 to it. And the reason we're adding 63 to it and not 64 is because we're starting on 64. $64 would get us to the start of the next one, of the next one, if that makes any sense. So that means that this is 192.168.1 point, and let's do that, okay? 64 plus 63 is 127. Which is our broadcast. Yes. Almost messed up again, but I didn't. Okay, so we add 63 to this because 64 is getting counted. And if we added 64, that gets us our next thing right here, which is going to be 128. So that means that 127 is our broadcast. That's our bro. Okay? And then we're going to add... Wow, I made this way more complicated than it needed to be. Each group is supposed to have 64, right? So that means every time you add 64, it should be each one. Man, I made this so much more complicated trying to figure out the network. So 64, yeah, 64 plus 64 is 128. Plus another 64, which is 192. Okay. So to clarify, where I was getting messed up is I was confusing the broadcast with the start of the next subnet. Okay, I wonder how many other people have that same problem. Okay, so to recap, we found the network and we found the broadcast. Our network, because it has here, and I'll use red. Okay, our network, because it is 64, because 2 to the power of 6 equals 64. Where I was getting confused is that is our block. That's our whole block. But 2 to the power of 6 minus 2 equals 62, and this is our usable. And one of these two is right here because that's our network. So all we really needed to do was figure out our block size to figure out how many addresses are in this subnet and then just add it to 0. So 64 add to 0 is 64. So that means that's our next one. 64 plus 64 is 128. And then 64 plus 128 is 192. That means that the broadcast of this is 127. The broadcast of this... No, the broadcast of this is not 127. It's 128. Shit.
Two will be 192.168.1.64/26. That's the network address, and here it is in binary. Notice that we changed one of the bits we borrowed from the host portion to a 1. So, the network address is now 192.168.1.64, with all of the host bits set to 0.
Oh,
now let's find
no,
the broadcast
I did it backwards. I said that the broadcast was going to be 127. The broadcast is 127 of this one. The broadcast of subnet 3 is 191. And the broadcast of subnet 4 is 255. I think I understand it, boys.
Address. Change all of the host bits to 1, and now let's convert it to dotted decimal. So, the broadcast address is 192.168.1.127. So that's the range for subnet 2. Add 1 to the broadcast address, and we'll get the network address for subnet 3. So that means subnet 3 is 192.168.1.128/26. Here is the network address in binary. Again, notice we changed one of the borrowed purple bits to 1, but the host bits are all 0. Change them to 1, and here's the broadcast address. So the address range for this subnet is 192.168.1.128 through 192.168.1.191.
Oh my god.
Now we can find the last subnet,
I understand
subnet 4. Subnet 4 is 192.168.1.192/26. Here is the network address in binary. This time the borrowed bits are all 1, so this is our last subnet. We don't have any room for more. Change the host bits to 1, and here's the broadcast address.
255.
So the address range for subnet 4 is 192.168.1.192 through 192.168.1.255.
Okay.
Okay, we found the answer to the quiz. You may notice something about these numbers. 0 plus 64 equals 64. 64 plus 64 equals 128.
Yes.
And 128 plus 64 equals 192. I said last video that I would just show you the basics of subnetting, not any special subnetting tricks, but let me show you just one that can help you figure things out faster. So, we found that a /26 subnet mask is appropriate. That's because there are 6 host bits, which allows 62 hosts. Let's draw this line here. On the left side is the network portion, and on the right side is the host portion. Since we're just looking at the last octet, let me make it bigger. Okay, so I've put the binary for just the last octet down here. Again, the red part is the host portion, and the purple part is the bits we borrowed to expand the network portion. You should remember the value of each binary bit, but let me put them up here anyway. From the right, 1, 2, 4, 8, 16, 32, 64, and 128. Notice that the last bit of the network portion is 64. This means that, to find the next subnet, we just have to add 64. Let's see. Add 64 and we get 192.168.1.64, which is the network address of subnet 2. Add 64 again, and we get 192.168.1.128, which is the network address of subnet 3. Finally, add 64 again, and we get 192.168.1.192, which is the network address of subnet 4. So, as you can see, by adding 64 each time, we were able to find the network addresses of each subnet. Now let's try another similar exercise. We have been given the 192.168.255.0/24 network, and have been asked to divide the network into 5 subnets of equal size. In this case, the number...
Okay. Where are we at? Number 3? Okay, let's get rid of this poo-poo. We don't need that poo-poo. Okay. And let's reset this. We'll go here. Alright. So what we have our network. 1, 2, 3, 4, 5. Okay, SW1, SW2, SW3, SW4, and SW5. Okay. The overall, man, I need to do this a different way. Okay. Oh my gosh, dude, stop pressing buttons. Okay, the network for this is 192.168.255.0/24. I'm going to let it finish kind of explaining, and then we're going to rock this one.
Number of hosts in each subnet hasn't been specified. So let's make 5 subnets that are as large as they can be. So all we have to do to solve this problem is find how many bits we have to borrow from the host portion. Currently, we are borrowing 0 bits from the host portion. That means that...
So our host portion is 24, which means that's a possible of... 2 to the 8th. Is that 255? Wow. Times 2 times... Yes, that's 255. Because 255 divided by 2... Damn it. 255 divided by... Gosh, dude. 255 divided by 2. I don't know what I'm doing anymore. Okay, hold on. Let's just let him explain instead of me trying to figure it out.
That we can't make any subnets. We just have one network, 192.168.255.0/24. If we borrow 1 bit, it now becomes a /25 network. Borrowing 1 bit also means we can make 2 subnets. Why is that? Well, all of the original network bits, the blue bits, cannot be changed. That is the network we received. However, the purple bit, the bit we borrowed from the host portion, we can change, and it can be either 0 or 1. If it's 0, we have the 192.168.255.0/25 network. If it's 1, we have the 192.168.255.128/25 network. The formula for the number of subnets is 2 to the power of x, and x is the number of borrowed bits. This is similar to calculating the number of hosts in a subnet, which is 2 to the power of n minus 2.
2 to the power of x equals the number of subnets. X is the number of borrowed bits. So 2 to the power of 1 is 2, so we have 2 subnets.
And n is the number of host bits. We subtract 2 for the network address and broadcast address, which can't be assigned to hosts. However, when calculating the number of subnets, we don't have to subtract 2, so it's simply 2 to the power of x, the number of borrowed bits. Anyway, we need 5 subnets, so borrowing 1 bit isn't enough. What if we borrow 2 bits like this? Well, 2 to the power of 2 is 4, so borrowing 2 bits allows us to make 4 subnets. Still not enough, we need 5, so let's borrow another bit. If we borrow 3 bits, how many subnets can we make? 2 to the power of 3 is 8, so we can make 8 subnets. So this is our answer. It's more subnets than we need just 5, but if we borrow only 2 bits and use a /26 mask, we won't have enough. As I said in the last video, you can't always make the numbers exactly match the number of subnets or number of hosts you need. So our first subnet will be 192.168.255.0/27. Here it is written in binary. Here's the network portion, and here's the...
Interesting. Wait, where's 1? Ugh, I hate when they're out of order. There we go. Okay. So let's use our little worksheet that's up here. We have 192.168, 250. Man, I always want to do 225. 255, 0. And we're doing /26.728. So that means all of these are taken, so that's 8. All of these are taken, so that's 8. all of these are taken, so that's 8. So we have 8 plus 8 plus 8 plus 3. So 8 plus 8 plus 8 is 24 plus 3 is 27. So I was wrong. So what does this mean? This means that the networks that's frozen is 27. That means this, the CIDR is 27. That means that this is 27. Okay, so that means that our mask is 255, 255, 255. And then we add 128, 64, and 32. $224. $224. So that means our wild card is 0, 0, 0. And then 1 plus 2 is 3. 3 plus 4 is 7. 7 plus 8 is 15. 15 plus is 31. Okay, so then this is our subnet. Okay. Our host, Socks, I need you to not. Our host is this. So 1, 2, 3, 4, 5. We have 5 bits free. So then it's 2 to the power of 5. I hate holding this thing. Okay, stay there. There's too much going on my desk. I'm about to throw you out. Oh, that's it. You're getting thrown out. Okay. Are you going to lay there? If you're going to lay there, everything's going to be fine. But if you're not going to lay there, it's not going to be fine. Okay. Two. How come I can't do power of? Is there no way to do a power of? It would just, where's the caret key? We don't believe in caret keys. Okay. One, two, three, four, 5. So it should be 32, right? That's not a toy, boy. Okay. Just gonna use the calculator on my phone. The one on the computer's just not working right. Okay. Is 32. Now, that's the amount of usable hosts. No, that's the amount of hosts in general. So that means usable is 30. So the octet that we split was the 4th octet. The masked value in that octet, which is what he's talking about, is 224. So then we have 256 subtract 224, which is 32. I do that correctly?
Here's the host portion. Let's look at just the last more subnets than we need. We need just 5. But if we borrow, what if we borrow 2 bits like this? Well, 2 to the power of 2 is 4. So borrowing 2 bits allows us to make 4 subnets. Still not enough. We need 5. So let's borrow another bit. If we borrow 3 bits, how many subnets can we make? 2 to the power of 3 is 8, so we can make 8 subnets. So this is our answer. It's more subnets than we need. We need just 5. But if we borrow only 2 bits and use a /26 mask, we won't have enough. As I said in the last video, you can't always make the numbers exactly match the number of subnets or number of hosts you need. So our first subnet will be 192.168.255.0/27. Here it is written in binary. Here's the network portion, and here's the host portion. Let's look at just the last octet once more. Here's just the last octet. What's the value of the last bit?
Okay, hold on. So that means that this guy is 7.
Bit of the network portion. It's 32. So using the trick I introduced before, we should be able to calculate the other subnets now. As I said before, subnet 1 is 192.168.255.0/27. Add 32, and we get
Okay, hold on. Oh, no. Whoa, 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 whoa. I want to do this. So that's our subnet 1. No, let's go up. So that means that so everything's just going to get plus 32. Plus actually, let's put that here. Everything's going to get plus 32 because of that. So that means that this is going to be 192 point. Well, you know what? I don't need to put all the other crap. I just need the last dot, the last octet. I just don't want to make the same mistake that I made last time. So 0 plus 32 is 32. Oh my God. Okay, 32. And then 32 plus 32 is 64. 64 plus 32 is 128. No, it's 96. .96. And then we're going to add 32 again, 128. Yes.
Subnet 2, which is 192.168.255.32/27. Add 32 again, and we get subnet 3, 192.168.255.64/27. Subnet 4 is 192.168.255.96/27. And subnet 5 is 192.168.255.128/27.
I did it.
Okay, we made up 5 subnets, as our requirements were to divide the network into 5 subnets. However, our /27 prefix length allows up to 8 subnets to be made from the address range. These 3 remaining subnets are 192.168.255.160.192 and .224/27.
And they're wasted because we can't.
Here's another type of subnetting question you might find. What subnet does host 192.168.5.57/27 belong to? So we have...
Okay. So what subnet does this belong to? That one has to belong to 192.168. .192.168.5.32. Hey, no. No. That is my wireless thing for my Xbox 360. And although the boys don't get on as much anymore. No. Stop it. Stop it. Get your paw from out from under there. No. Okay. Oh, we're done. Okay. Yes. Look at him. He wants to do subnetting too. Can you meow? We meow? Meow. Okay. He's like eating my phone charger and stuff up here. Okay. So this has to belong to 192.168.5.32/27. And the only reason I'm saying that is because if we divide it all based off of what we just did, this address has to fall inside this subnet because this is the network and the broadcast goes all the way to 0.63.
Have the IP address of a host, 192.168.5.57, and we don't know the network address of the subnet. Let's see how we can figure this out. It's actually a fairly simple process. Here's 192.168.5.57 in binary and dotted decimal. However, it's /27, so let's show the borrowed bits. These 3 purple bits are borrowed and added to the network portion. Now, to find the network address, we simply need to change all of the host bits to 0. Now, the last octet is 00100000. Change that back to dotted decimal, and you get 192.168.5.32. So that's...
No way he just did that. No way he just did that.
That's the answer. Change that back to dotted decimal, and you get 192.
No way it's that simple. I'm over here like trying to like do crazy math equations because what he just figured out was the target octet. And the way you get that, how's the block size? Man.
192.168.5.32. So that's the answer. The host, 192.168.5.57/27, belongs to the subnet 192.168.5.32/27. Let's do one more for practice. What subnet does host 192.168.29.219/29 belong to?
Well, based off of what he just did. Well, hell, like obviously his way is way better. Like that was like way simple. So then if we use his method, his way, all we have to do is figure out what's frozen, what's not frozen. So 192.168.29.219.29. 29. So then we just got to figure this out. 24 25, 26, 27, 28, 29. Stupid, dude. I hate this thing. After stream today, I'm going to figure out how to never use this again. Okay. So we just change it all to zeros? No, there's no way. That would mean that it would be 8? Is that right?
Pause the video now and try to figure out the answer for yourself.
I think it'd be 8.
Okay, let's check. Write out the address in binary first. Identify where the network part ends.
Yes.
In this case, 5 bits are borrowed from the host portion and added to the network portion. Set all of the host bits to 0, and then convert back to dotted decimal. There's our answer.
Oh, that's how he did it. It's not that okay.
Set all of the host bits to 0.
So he just turns these to 0. So this just needs to be a big old fat goose egg. And then we need to figure out what bits are left. So since it was 1, 1, 0, 1, then we just add these bits up. And that tells us what network we're in, what our host network is.
And then convert back to dotted decimal. There's our answer. So, host 192.168.29.219/29 belongs to the subnet 192.168.29.216/29. Okay, let's review some numbers. This is a table of the different subnet sizes for Class C networks. For example, with a /25 prefix length, you divide the network into 2. There are 2 subnets. Also, each subnet can contain 126 hosts. I recommend that you memorize these numbers. It will help you perform subnetting faster and easier than if you have to calculate everything every single time.
Yeah.
Although these are fairly simple to calculate. For the number of subnets, each additional bit that you borrow doubles the number of subnets. For number of hosts, each host bit doubles.
Hold on 1 second. I had to get some peanuts. I'm hungry.
Doubles the amount of hosts, except you have to subtract 2 for the network and broadcast addresses. Take note of /31. The number of hosts is 0. I mentioned this in the last video, but it's because there is only a single host bit, so there are only 2 possible addresses, which are taken by the network and broadcast address. However, for a point-to-point connection, you can actually use a /31 and assign those 2 addresses to each end of the connection, and have no network or broadcast addresses. Also, /32 technically uses all bits for the network address, allowing no hosts, but you can't assign a /32 mask to identify a specific host when writing routes and such, and in some other special cases. Now let's finally take a look at subnetting some larger networks, specifically Class B. Looking at this chart again, you can see that there are many more host bits, and therefore many more possible subnets that can be created with a Class B network than with a Class C network. However, the process of subnetting is exactly the same. So I'll just walk you through a couple examples with Class B networks, and then we'll leave Class A networks for the last video of this subnetting series. You have been given the 172.16.0.0/16 network.
Okay.
You are asked to create 80 subnets for your company's various LANs. What prefix length should you use? Okay, this is really a simple question, and we can follow the exact same process as last time. Pause the video here if you want to try it by yourself.
No.
Okay, let's figure it out. Again, we can simply use the 2 to the power of x formula, where x is the number of borrowed bits. If we borrow no bits, we can't make any subnets. We just have one large /16 network. If we borrow 1 bit, we can make 2 subnets, because 2 to the power of 1 is 2. This gives us a prefix length of /17, and if we write the subnet mask in dotted decimal, it is 255.255.128.0. Remember, when you enter commands in the Cisco CLI, you can't use the CIDR notation like /17. You you have to enter dotted decimal like 255.255.128.0. Anyway, 2 subnets isn't enough for our needs, so let's borrow another bit. Borrowing 2 bits allows for 4 subnets. This is a /18 prefix length, and the subnet mask is written as 255.255.192.0 in dotted decimal. Let's borrow another bit. Borrowing 3 bits gives us 8 subnets, and a /19 prefix length. The subnet mask is 255.255.224.0 in dotted decimal. Still not enough subnets, so let's borrow another bit. Borrowing 4 bits allows us to create 16 subnets, and uses a /20 prefix length. /20 is 255.255.240.0 in dotted decimal, by the way. Borrowing 5 bits gives us 32 subnets, and the prefix length is /21, which is 255.255.248.0 in dotted decimal. Borrowing 6 bits gives us 64 subnets. Getting close. The prefix length is /22, which is 255.255.252.0 in dotted decimal. Let's borrow 1 more bit, which should be enough. Borrowing 7 bits gives us 128 subnets. The prefix length is /23, which is 255.255.254.0 in dotted decimal. So, this is the correct answer. We should use a /23 prefix length so we can create the 80 subnets we need. 128 subnets is more than we need, but /22 only allows for 64, which is not enough. I won't show you all 80 subnets, of course, but let's look at some of the subnets that can be made. The first being 172.16.0.0/23, of course. The next is 172.16.2.0/23. Notice I changed the last bit of the network portion to 1. Next is 172.16.4.0/23. Then 172.16.6.0, 172.16.8.0, etc. Let's do another similar question. You have been given the 172.22.0.0/16 network. You are required to divide the network into 500 separate subnets. What prefix length should you use? Pause the video and try to figure this one out for yourself, and I'll show you the answer in the next slide.
So we're going to divide this to 500 separate subnets. Oh, no. You've been given 172.22.0.0/16. And we need to divide that into 500 subnets. I think it's 2. That was just quick math in my head.
Okay, let's go to the next slide. So the correct answer is /25. We need to divide this class B network into 500 subnets. So that means we have to borrow 9 bits, because 2 to the power of 9 equals 512. Notice that you can borrow bits even from the last octet, so you can use /25, /26, /27, etc., even with the class B network. Here's another practice question. You have been given the 172.18.0.0/16 network. Your company requires 250 subnets with the same number of hosts per subnet. What prefix length should you use? This time you have to consider both the number of subnets and number of hosts. Once again, pause the video to solve this yourself, and then I'll give you the answer in the next slide. Okay, let's check out the next slide. So the answer is /24. We need 250 subnets, and borrowing 8 bits allows us to make 256 subnets. We also need 250 hosts per subnet, and having 8 host bits allows for 254 hosts per subnet.
So we're basically subnetting
Okay,
a subnet.
before moving on to the quiz, let's do one more identify the subnet problem, this time with a class B network. What subnet does host 172.25.217.192/21 belong to?
Well, if we do it his method, One 172 25. Nope, not 1. 217 192 21. So that's 8 16 17 18 19 20 21. So we divide it right here. And then we figure out what the binary is. So the binary is going to be 128 definitely plus 64, yes, plus 32, no, Plus 16. Yes. Plus 8. Yes. And then that gives us 216, so it needs 0, 0, 1. So then we drop these and we just add this up, which is 216, not 17. So that means that this is going to be 172.25.116.0. Right?
The process is exactly the same as with the Class C network. Write out the address in binary, change all of the host bits to 0, and then change it back to dotted decimal. Pause the video if you want to try it on your own. Okay, let's check the answer. Here's the address written in binary. As usual, the red bits are the host bits, and the purple bits are the borrowed bits, which are now part of the network portion. Change the host bits all to 0, convert it back to dotted decimal, and you get 172.25.216.0.
Yeah, that's what I got.
So, there's the answer to the question.
Whoa, let's go!
172.217.192/21 belongs to the 172.25.216.0/21 subnet. The process was exactly the same as for a Class C network. There are just more host bits. Here's a chart like the one I showed you for Class C addresses, showing the number of available subnets and the number of available host addresses for each prefix length when subnetting a Class B network. Don't worry, it's not necessary to memorize these numbers. That would simply be a waste of effort. Just know the patterns. For each borrowed bit, the number of subnets doubles, 2, 4, 8, 16, 32, etc. For each host bit, the number of addresses in each subnet doubles. However, you have to subtract 2 to identify the number of usable host addresses. As I said, don't memorize this. Just know these patterns so you can calculate these when you need to. Okay, let's move on to today's quiz. I will give you 5 questions following the same pattern as the ones we solved in today's video. Please post your answers in the comment section of this video. I will give the answers and explanations at the beginning of the next video.
Okay, so my goal is to answer these questions the way he is provided and then make sense with it when it comes to the block size and the target octet.
Question 1. You have been given the 172.30.0.0/16 network. Your company requires 100 subnets with at least 500 hosts per subnet. What prefix length should you use? Pause the video to find the answer.
So, okay. Actually, it'll be way easier if we just delete it and then make another one. So let's see here. We have 172.30.0.0/16. So that means all of these bits are taken. Okay. So, well, that makes it look like it. Yeah, look at that. Okay. So, we need to figure out how many of these hosts we need to borrow. And when we borrow, what we do to the power of that thing, and then that should tell us. So, like, if we borrow 1, that's 2 to the power of 1, so we gain 2. So, let's start with a bigger number, like 8. So, we do 2 to the power of 8, that gives us 256. Or is that host, or am I getting that mixed up? So 2 to the power of 10, way too much. 2 to the power of 9, that's it. So we need this many hosts. So that would be 16 plus 9, 25. So /25. So is that 255 point, and this is a slash, 128. Is that, or does it just want to know the prefix? I should have grabbed more peanuts.
Okay, let's go to question 2. What subnet does host 172.21.111.201/20 belong to? Pause the video to find the answer.
What?
Okay, let's go to question 2. What subnet does host 172.21.111.201/20 belong to?
Okay. Whoa, but I want to know the answer.
As the ones we solved in today's video. Please post your answers in the comment section of this video. I will give the answers and explanations at the beginning of the next video. Let's go to question 1. You have been given the 172.30.0.0/16 network. Your company requires 100 subnets with at least 500 hosts per subnet. What prefix length should you use? Pause the video to find the answer.
I think it's 25. We're going to check
Okay, let's go to question 2. What subnet does host 172.21.111.201/20 belong to? Pause the video to find the answer.
Okay, we'll just make another thing, and then we'll hide it. Okay, let's do this one. One 72, 21, 123, 201/20. So 16, 17, 18, 19, 20. So here is our divide. Okay. So that's going to be 1, 3. Actually, no, let's not start from that side. Let's start from this side. 64 plus 32 is 96 plus 16, which is 112. That doesn't work. So that's going to be 0. So we're going to add... Whoa. No, that doesn't work. So 8.
The first answer is not /25, it is /23. /25 gives you 512 available addresses.
Okay. The first answer is not /25, it is /23. /25 would give you
/23.
Okay. So you're telling me that I overshot it. Let's look at it. This should give us... So if I'm calculating this correctly, that should be 2 to the power of 9, right? 2 to the power of 9. You're correct, which would be 512 addresses. So then it needs to be /2023. That's a good catch. 2 to the power of 7. No. The question is your company requires 100 subnets with at least 500 hosts per subnet. So it doesn't matter if we broke 500 because it needs at least 500. That's why I thought it was 25 and not 23. Unless I'm confusing available addresses with hosts per subnet. Unless I'm confusing some type of terminology. All right. Go back here. I could still be wrong. We'll look at the answer when I'm done. So then this is going to be 64 plus 32, which is 96. So this is going to be 96. .0/20. That's the host. That's the network. 90. I guess I have a spot for it. That looks like a 6. 21.172. Yeah, maybe. Okay, well, let's move on to the next one. When I'm done with all of them, we'll go and check them.
What is the broadcast address of the network 192.168.91.78/26 belongs to? Pause the video to find your answer.
Okay, so we have... Whoa, what's going on? No, deselect. Why are we selecting things? Okay, let's see here. 192.168.91.78/26. So 8, 16, 24, 25, 26. Okay. And then 78 is going to be six. Let's see here. 64 plus 32. No. No. Seven two plus 4 plus 2. Okay. That's a 0. So then 64. No. Okay, I think that's correct.
Okay, let's go to question 4.
Last one.
You divide the 172.16.0.0/16 network into 4 subnets of equal size. Identify the network and broadcast addresses of the second subnet. Pause the video to find the answer.
Into 4 equal subnets. I'm not sure. So we need to take this into 4. So this is... Okay, I'm not going to answer this one because this is similar to the first one that I possibly may have gotten wrong. So we're going to go... check the answers.
Welcome to Jeremy's IT Lab. This is a free, complete course for the CCNA. If you like these videos, please subscribe to follow along with the series. Also, please like and leave a comment and share the video to
What is going on?
help spread this free series of videos. Thanks for your help. This video will be the last of the subnetting series. Okay, here's question 1 from the last video. You have been given the 172.30.0.0/16 network. Your company requires 100 subnets with at least 500 hosts per subnet. What prefix length should you use? This is a simple one. How many bits do we have to borrow to make 100 subnets? You can just count on your fingers. Borrowing 1 bit allows for 2 subnets. Borrowing 2 bits allows 4 subnets. 3 borrowed bits allows for 8 subnets. 4 borrowed bits allows for 16 subnets. 5 borrowed bits allows for 32 subnets. 6 borrowed bits allows for 64 subnets. And 7 borrowed bits allows for 128 subnets. So we need to borrow 7 bits to create enough subnets. Does that leave enough host bits for at least 500 hosts?
Damn.
Let's check. So, borrowing 7 bits means we will use a /23 prefix length, which leaves 9 host bits. Once more, the red bits are the host bits. 9 host bits allows 510 usable addresses, which is enough for the 500 we need.
So what I'm getting confused with is host bits and usable addresses. I'm getting that stuff mixed up. I'll have to mark that down. We'll do that in the review session on Sunday.
To question 1. The prefix length will be /23. /23 is written as 255.255.254.0 in dotted decimal, by the way. As I mentioned before, make sure you know how to write different prefix lengths in dotted decimal too. Let's go on to question 2. What subnet does host 172.21.111.201/20 belong
I think
to?
I got this one correct.
These questions are easy if you remember the steps I taught you. First, write out the address in binary like this. Then, change all of the host bits to 0. Convert the address back to dotted decimal, and that's the answer.
Yes.
So, host 172.21.111.201/20 belongs to the subnet 172.21.96.0/20. Let's check the answer for question 3 next. What is the broadcast address of the network 192.168.91.78/26 belongs to? So to solve this problem, you follow the same steps as for the previous question, except instead of changing all host bits to 0, you change them to 1. Let's try it out. Write out the address in binary. Then, since we're looking for the broadcast address, not the network address, change all of the host bits to 1. Convert the address back to dotted decimal, and that's the broadcast address for the subnet.
I missed
So, the answer for question 3 is 192.168.91.127. That's the broadcast address for this network.
Okay, I misunderstood. I did it the same way as the last one.
Let's check the answer for question 4. You divide the network 172.16.0.0/16 into 4 subnets of equal size. Identify the network and broadcast addresses of the second subnet. So the first step to solving this question is to determine the prefix length we must use. To divide the network into 4 subnets of equal size, we have to borrow 2 bits, because 2 to the power of 2 is 4. So when we borrow 2 bits, that makes...
So when we're looking for... Here, go back. So when we're looking for the subnets, the amount of subnets, that's the amount of bits that we have to borrow?
We have to borrow 2 bits, because 2 to the power of 2...
Yes. Okay, so we have to borrow 2 bits because 2 to the power of 2 is 4 subnets. So for that 100, we just keep borrowing and borrowing until we hit the 100. Or the 500.
Is 4. So when we borrow 2 bits, that makes a /18 prefix length. Change this last bit to 1, and write it in dotted decimal again. 172.16.64.0. This is the network address of the second subnet. Now, to find the broadcast address, simply change all of the host bits to 1. So the broadcast address is 172.16.127.255. So these are the answers to question 4. Finally, question 5. You divide the 172.30.0.0/16 network into subnets of 1,000 hosts each. How many subnets are you able to make? Well, to know how many subnets we are able to make, we have to know how many bits we can borrow. But to know how many bits we can borrow, we need to find how many host bits we need for 1,000 hosts. We will need 10 host bits for 1,000 hosts, because 2 to the power of 10 minus 2 allows for 1,022 hosts. That will leave us with 6 borrowed bits.
Wow,
6 borrowed bits means we can make 64 subnets. So that's the answer to question 5. Okay, let's get to subnetting Class A networks.
Okay.
Look at the
we're gonna stop that. That video will be on Monday. I just wanted to know the answers to this stuff and figure out why I was wrong. So let me process this for a second. Host is the addresses that we need, right? Subnets have those addresses, is the grouping of the addresses. And that is controlled based off of where we divide the octet, if we divide it at all, based off of bits that are frozen and hosts that are free. Yes. Okay. We're gonna practice on 1. Oh, good. This will be the last thing that we do today. Okay. One 169 54 26 80/19. So it's 8 16, 17, 18, 19. So that means that these are frozen. Okay, so then let's start filling it out. This is easy. These are give me's. These are just making sure that we understand the vocabulary. So the networks that are frozen is 19. So that means the CIDR is 19. That means that it's 8 plus 4 plus 0 plus 0, which is 19. The mask is 255. What is 128 plus 64 plus 32 plus 16? 240. 240, 0, 0. So then that means the wild card is going to be 255. 255. And then 15. Okay. The octet in question is octet 2. Mask value in that octet.
You are in the wrong octet for /19.
Oh shit, you're right. I miscounted. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. I don't know what I was thinking. I'm tired. So I mean, honestly, that means that all this is wrong. Let's just start over. This is where we're at. Okay. So 26. Would be 16. So these would be zeros. So that means that the interesting octet is 3. We're at 19, 19. We have 8 plus 8 plus 3. Now that equals 19. 16, 17, 18, 19, 0. Thank you very much. Thank you very much, Rube. Okay, here we go. So that means that's going to be 255. Same. Not same. That looks like an 11. There we go. I need to make this bigger so that way it's easier to write in. 158 plus 64 plus 32. Dang it, dude. I hate when my calculator does that. 128 plus 64 plus 32. Dude, the spam calls, bro. The spam calls. They're nuts. Like, I've already gotten 4 in the last, like, 10 minutes. So then this should be 224. Right? 0. And the wild card would be 255. And then 17. So then the host bits is going to be 8, 9, 10, 11, 12, 13. So 2 to the power of 13. So our addresses that are free is 8,000. That looks like not an 8. 8,192. Our usable ones is going to be 8,190. So then where I struggle was to figure out this thing, the target octet rounded down. But I feel like that's what he just kind of did in the video to make things easier. So the host has got to be 169, 169, okay, 169, 169, 169. That's easy. And then it's got to be 54, 54, 54, 54, 54, 54. And then where it changes is right here. So what he did is that he added all these together to find the host. Isn't that what he did? No. He put one right here. So the host would be 32. But that doesn't make any sense. The host can't be 32 because we have 26. Did I miscount again? 16, 17, 18, 19. No. So the way I was doing it, not counting the video that we just watched, is that the mask value in the octet should be 224. So then if you do 224, sorry, 256, subtract 234, you get 32. Holy shit. How is that? How is that possible? So you're telling me that the host is going to be 169.54.32.0?
Always remember the magic numbers 128, 64, 32, 16, 8, 4, 2, 1. In this case, the first network is from 0 to 31 and 32 to 63 is the second network.
Okay. Always remember the magic numbers, right? Okay. In this case, the first network is from 0 to 31. And 32 to 63 is the second network. So you're telling me that the network right here is 31? Oh shit, I typed it in wrong. No, I didn't. No, I typed it in correctly. How is it not? Okay, so then why did this tell me 0? Why did it tell me that the network was 0.0? See, I just have to figure out the network. If I can figure out the network, then I can figure out everything else. That's what this thing has to do. This thing has to do something with, like, you multiply something to try to get it as close to it as possible. Okay. All right, we're asking.
Since 0.26 is in that range from 0.0 to 0.31.
So 0.0 to 0.31 is the, oh. 0.0 to 0.31 is the first network, and 0.32 to 0.63 is the second network. So, okay, I'm following you. So then, how do I find the ultimate network, like the one that's ahead of it all? The block size is 32. How do I know that 0.0 is the network? Is it because I know that it's 32 and I subtract 32 and then that gives me 0 because 32 minus 32 is 0? Okay. There we go. Ah, I missed it. Okay. Okay, I understand kind of why the block size is 32. But I am not following fully why the okay. Why the network is 32 and how that translates to the network being 0.0 and how that connects to the target octet. Okay, let's give it some more context. That way it gives me a little bit better of an answer. I have learned that if you go to the last bit of the frozen network bits in the last octet, that is the block size. So is that the size of the network? No, it can't be the size of the network. I am also struggling with the amount of addresses and hosts and subnets when subnetting a subnet. Okay, let's see what it says. I think that was enough context. That basically sums up like my constant mix-ups. All right, let's let it cook. Let's let it cook, boys. Since point 26 is in the range of... Okay, this is making sense. Since point 26 is in the range of 0.0 to 0.32. Okay, that makes sense. But my question is then, how do I get the actual network? How do I get 0.0? How do I know that? Is that because... So that... It's just not making sense why the network is 169.54.0.0. That looks like a 6. It makes sense in the terms of like why this is 26, but it doesn't make sense because the octet is split. Thought for 1 minute and 34 seconds. Fantastic. All right, speak to me, Claude. I knew I should have kept Cortana. What are we doing? Why are we just thinking? You said thought. No, it's still thinking. Lame. So maybe I can figure it out on my own. This has something to do with we take the block size and we see how many times it can go into it. Look, I have these notes. Let's see. What does this say? A multiple of the block size down to a multiple of the block size. So then we have to multiply this. How many times 26 goes into 32? Well, it goes into it 0 times. That would make sense. Okay, Claude, why have you forsaken me? Nice! Wow, that like never happens. Claude never does that. Chatbot GPT will do that. Clarifying. We're going to let it cook a little bit longer. We don't really have a choice, right? Dude, it is not. I think my internet's bad. Yeah.
To visually grasp it, do it in binary by ones in network and zeros in host with A/19 network.
Okay. To visually grasp it, do it in binary by ones in network and zeros in host. And then with the /19. Oh, and that's what he was doing in the video too. Where he was making all of these zeros, or then all making them all ones. Watch pot never boils. Visually grasp it. I think where I'm getting confused is I thought that host and network were kind of the same thing. No, I didn't. But maybe I don't know. I think that's where I got it confused. Here we go. Please give me an explanation.
Your heuristic is actually correct. The last frozen bit in the interesting octet is worth 32, and that is the block size. The slip is one small step after that. 32 is how wide each subnet is, not where yours starts. Networks fall on multiples of the block size, 0, 32, 64, 96.
So this is how big the subnet is? I think this is what you were just talking about. Last kept bit is worth 32 block size. Octet size target 26. Network address equal keep the purple bits 0, the gray ones out. Yeah. I know that. The network 196.52.
Be patient with it. Subnetting is difficult. I'm getting close to taking my CCNA too.
Thanks, man. Good luck for you. Good luck. The post at the start of the 26th block. What? No. Give me back the visual. What? You had an amazing visual. I was alert. Oh, I'm so upset. Okay, I'm going to figure this out off stream. I'm going to end it there. And I'm going to come back to you guys. Well, we'll read it together first.
Your binary on the worksheet already proves this. You wrote 26 as 00111010 and drew the line after the third bit.
Okay, no, we're not going to read this. I don't know. Something weird happened with Claude. I don't know why it did. I don't know. Anyway, we're going to end it there. We'll come back. There will be a study session on Sunday where we're going to do this. We're not going to go any further. We're just going to be working on day 13 and day 14 of subnetting and stuff like that, and figuring all that stuff out. I have it originally saying that we're going to review the OSI model and the TCP. We might do that as well, but we're definitely 100% going to be doing this. And honestly, we'll probably be reviewing this for a while. So I hope you learned something. I hope you enjoyed it. If you haven't already, please subscribe. Subscribe to me, and definitely subscribe to Jeremy's IT Lab. Amazing. He's amazing. Okay. He's definitely teaching me a whole bunch of stuff. So that's it. That's all I got. I hope you enjoyed it. I hope you all the stuff. I will catch you tomorrow night for the gaming stream if you are into that, or on Sunday for the review session. Remember, work with what you got, build what you need, and I will catch you in the next one.